All right, so the goal of this video is to prove some results to determine whether or not polynomials are irreducible or reducible. So these are just some basic results. They're not going to cover all possible polynomials, but they'll at least give us a sense of whether or not certain kinds of polynomials are reducible or irreducible. So before we begin proving our results, we need to establish a few pieces of information or a few definitions. So I'll start with R, a commutative ring, and I'll take some polynomial, f of x and r bracket x. And this polynomial induces a function f from r to r. So if the polynomial has this form, if it's a0 plus a1x plus dot 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 plus anx to the n, I can define this function f and define f of r to be a0 plus a1r plus dot 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 plus anr to the n for all r and r. And the idea is essentially we're plugging in for x. That's kind of the way to view this. And so let's look at a quick example. So I'm going to first consider the function f of x in q bracket x. This is a polynomial with rational coefficients. And the polynomial I'm going to consider is f of x is x squared plus 1. And so what am I essentially doing? I'm just defining a function that says, well, I can plug into this polynomial, right? So for example, f of 0 is just 0 squared plus 1, which is 1. F of 2 is just 2 squared plus 1, which is 5. And in general, f of r is going to be r squared plus 1 for every rational number r. So let's look at one more example. So I'm going to consider the polynomial f of x is 2x to the fourth plus 2x, and g of x is 2x cubed plus 2x squared, both in z3 bracket x. And the first thing I'll point out is that these two polynomials are different polynomials, right? These two are completely different polynomials. They don't even have the same degree, right? F of x has degree 4, g of x has degree 3. One thing I will point out, though, is that the function that they induce is the same function. So let's take a look. If I compute f of 0 is going to be 2 times 0 to the fourth plus 2 times 0. So that's 0. F of 1 is going to be 2 times 1 to the fourth plus 2 times 1. So that's going to be 2 plus 2, 4, which is equal to 1, right? Because we're working in Z mod 3. And then I can look at f of 2, and this one's a little bit trickier because the numbers get bigger, but it's 2 times 2 to the fourth plus 2 times 2. So this is going to be 32 plus 4, so it's 36. And I might notice that this is equal to 0 mod 3. Okay, so f of 0 is 0, f of 1 is 1, f of 2 is 2. Now let's take a look at g. If I compute g of 0, I'll get 2 times 0 cubed plus 2 times 0 squared, so that's 0. If I compute g of 1, I'll get 2 times 1 cubed plus 2 times 1 squared. So that's going to be 4, which is equal to 1. So g of 1 is equal to 1. And g of 2, this is going to be 2 times 2 cubed plus 2 times 2 squared. So this is going to be 16 plus 8, which is 24, which is 0, right? And so the observation to make is that these induce the same function even though they are distinct polynomials, right? So the idea is that the function you create from two distinct polynomials might be the same function, right? Both of these map 0 to 0, 1 to 1, and 2 to 0. So these are the same function. So I've taken a second to write out this fact, right? The idea, again, is that f of 0 is 0, f of 1 is 1, f of 2 is 0, and g of 0 is 0, g of 1 is 1, and g of 2 is 0. And so the idea is that as functions from z3 to z3, we have that f of r is equal to g of r for all r in z3, which means by definition that these two are equal as functions, right? So even though the polynomials are different, the function that they induce is the same. Okay, so now we're ready to define the notion of the root of a polynomial, and it's the same notion you might remember from a high school algebra class or something like that. So we'll let R again be a commutative ring and f of x be a polynomial. A root of f of x is just an element of our ring R, an element A of our ring R, such that f of a is equal to 0. And I guess I should have a 0 sub r over here. It's the 0 element of my ring. So let's look at a quick example. If we consider the example g of x is equal to 2x cubed plus 2x squared from earlier in z3 bracket x, one thing we might remember is that g of 0 is equal to 0 and g of 2 is equal to 0. So we know that 0 and 2 in z mod 3 are roots. So we would just say that these are roots of g of x. Okay, so these are roots of my polynomial. What about some other examples? Well, what if I consider the polynomial f of x is equal to x squared plus 1 in r bracket x. One thing that I might notice is that this has no roots in r. Right? This has no roots in the real numbers, since I know that for all r and r, for every real number r squared plus 1 is always bigger than 0. Right? I know that this will never equal 0. So this is a polynomial that has no real roots. But if I change the ring that I'm working with, for example, if I take f of x is equal to x squared plus 1, and I view it as an element of c bracket x, right? Because the coefficients are real numbers, so they're automatically complex numbers. This has roots I and negative I, right? I being the square root of -1. And in particular, I have f of I is I squared plus 1, which is -1 plus 1, which is 0. And similarly, f of negative I is going to be negative I squared plus 1, which is -1 plus 1, which is equal to 0. Okay, so this is just our usual notion of root of a polynomial, right? And I guess I should say that I and negative I are elements of C, because these are complex numbers, but not real numbers. Okay, so now we're ready to prove some results. We've established some definitions and we can start proving some theorems. So this is going to be our first result. So we're going to assume that f is a field. I'm going to take f of x to be a polynomial whose coefficients are in my field f, and I'm going to let a be an element of my field. And the question I'm going to ask is, what happens when I take f of x and divide it by x minus a? What is my remainder? And this theorem is kind of nice. This theorem tells me that f of a is going to be the remainder when the polynomial f of x is divided by x minus a. So how can we prove such a theorem? Okay, well, the first thing I know is that by the division algorithm, I can write f of x is equal to x minus a times some quotient plus some remainder, right? So I could write f of x as x minus a times q of x plus r of x, where I know that both q of x and r of x are elements of f bracket x. And in particular, I know that the degree of r of x is less than the degree of x minus a, or r of x is 0. But let's kind of think about this. I know that the degree of x minus a is 1. That's a degree 1 polynomial. So what is this really telling me? It's telling me that the degree of r of x is 0, or r of x itself is 0. So if I look at this information, this is really telling me that r of x is equal to c for some c and f, right? It's telling me that my polynomial is a constant polynomial. A degree 0 polynomial is one that's a constant polynomial. Or my polynomial is just the 0 polynomial. Okay, so I have something about my remainder. Well, what can I then say? Then, if I look at f of a is equal to a minus a times q of a plus r of a. And then I might notice, wait a second, a minus a is just 0 times q of a. And I know r of a is equal to c. And so what does that tell me? That tells me that f of a is equal to c. So f of a is equal to my remainder, r of x. Okay, so that tells me that f of a is equal to r of x, and I've completed my proof. Okay, so we're ready to look at some examples now. So I'm going to consider this polynomial f of x as x to the 42 minus 2x cubed plus 5. And I'm going to ask the question, what is the remainder when f of x is divided by x minus 1? So my theorem above tells me that all I need to do to find this remainder is to compute f of 1, right? So the remainder, according to my theorem, is just going to be f of 1. And f of 1 in this case is going to be 1 to the 42nd power minus 2 times 1 cubed plus 5. And what does that equal? This is going to be 1 minus 2 plus 5. And that gives me an answer of 4. Right? So this is my remainder. My remainder is 4. So when I take this big polynomial, x to the 42nd minus 2x cubed plus 5 and divide it by x minus 1, the remainder will be 4. Okay, so here's another similar problem. I'll take f of x to be x cubed plus 3x squared plus 2x, and this will be a polynomial whose coefficients are in z mod 5. And we're going to ask, what is the remainder when f of x is divided by x plus 2? And the first thing I'm going to observe is that x plus 2 is equal to x minus negative 2. Right? So the remainder that we're after is going to be given by f of negative 2. Right? The theorem above tells me I need to I'm dividing by x minus a. So technically here I'm dividing by x minus -2. Okay, so let's compute f of -2. So f of -2, this is going to be, well, it's -2 cubed plus 3 times -2 squared plus 2 times -2. What does that leave me with? This is -8 plus 12 minus 4. And I see that this is 0. So my remainder is 0. All right, so my remainder is 0. And what does that tell me? This tells me right away that x plus 2 divides this polynomial x cubed plus 3x squared plus 2x. If I want to find the quotient, I have to go and do polynomial long division. But this at least tells me that x plus 2 divides this thing, so I know that I'll be able to factor x cubed plus 3x squared plus 2x as x plus 2 times some quadratic polynomial. But in particular, what I notice is that x cubed plus 3x squared plus 2x is a reducible polynomial. Right? This is not an irreducible polynomial. So finding a root tells me right away that I can factor this polynomial. So this leads us naturally into the following theorem. We'll say let f be a field, f of x be an element of capital F bracket x, and a be an element of capital F. We'll say that a is a root of the polynomial f of x if and only if x minus a divides f of x. So this is a pretty straightforward proof given our previous result. So let's prove this. I'll say suppose a and f is a root. What does that tell me? Well, then I know that f of a is equal to 0. And by our last theorem, so by the last result, I can then say that, well, the remainder, when I divide, so when f of x is divided by x minus a, is 0. And what does this mean? In other words, this means that x minus a divides f of x. All right, so we've proved the forward direction. All right, so now we're ready for the backwards direction. So I'll say, suppose x minus a divides f of x. Well, we can apply our definition of divisibility here. All right, so I could say then there exists some polynomial g of x in f bracket x, right, by definition of divides, such that f of x is equal to x minus a times g of x. Well, then if I plug in x equal to a, I'll get a minus a times g of a. In other words, I'll get 0 times g of a, which is just equal to 0. So I know that a is a root of f of x. Okay, and this proves our result. So now we're ready for some examples. So we'll use our theorem now to do the following example. We'll take this polynomial f of x to be x to the 6th plus x to the 5th plus x to the 4th minus 3x squared plus x minus 1 in q bracket x, and I want to show that this polynomial is reducible. So one way to show that the polynomial is reducible is to use the theorem above and to try to find the root of the polynomial. Because if I can find a root of the polynomial, then I have a linear factor of the polynomial. So I might get lucky and plug some numbers in and realize that, oh, x equal to 1 is a root. So one thing I might notice is if I compute f of 1, this is going to be 1 to the 6th plus 1 to the 5th plus 1 to the 4th minus 3 times 1 squared plus 1 minus 1. And if I think about this, this is 1 plus 1 plus 1 minus 3 plus 1 minus 1. I'll see that this equals 0. So by our theorem above, I know that the remainder, when I divide by x minus 1, is going to be 0. So I know x minus 1 is going to divide f of x. In other words, f of x can be written as x minus 1 times g of x, where I know that the degree of g of x has to be, well, if f of x has degree 6 and we have a linear factor, then the degree of g of x has to be 5, right? And now, since I've written f of x as a product of smaller degree polynomials, I know that f of x is reducible. So one natural question to now ask is, if I have a polynomial of degree n, how many roots does that polynomial have? Or what's, can I say anything about the number of roots that that polynomial might have? So what I'm going to do is I'm going to, again, assume that capital F is a field and take f of x to be an element whose coefficients are in capital F. And I'll assume that the degree of f of x is n, where n is some natural number bigger than or equal to 0. The theorem says that f of x has at most n roots in f, right? So if I'm working with a polynomial whose coefficients come from a field and I'm looking for roots in that field, the number of roots I'll find is capped or upper bounded by the degree of the polynomial. And we're going to see in a second that this theorem actually fails if you're not working over a field. Okay, so let's prove this theorem. So how does the proof go? The proof is actually a proof by induction on the degree of the polynomial. So I'm going to induct on n. So our base case is n is equal to 0. And then I have to ask myself, well, what are the degree 0 polynomials? The degree 0 polynomials are the constant polynomials. And we remember that the 0 polynomial, the polynomial f of x equals 0, is not assigned a degree. So when I'm talking about a degree 0 polynomial, I mean a non-zero constant polynomial. All right, so here I'll say that f of x is equal to c for some c in my field that's non-zero. Well, if I think about this polynomial, no matter what I plug in, this polynomial is never going to equal 0, right? F of a is always going to equal c, no matter what a from f I choose to plug in. So the base case is kind of trivial. Basically, if the polynomial is a non-zero constant, then it has no roots. So it has at most 0 roots. Okay, so now we're ready for the inductive step of the proof. So I'm going to suppose for some n greater than or equal to 0 that any polynomial of degree n has at most n roots. And what I'm going to do is I'll say let f of x be a polynomial and suppose that the degree of f of x is equal to n plus 1. Okay, so we have two possibilities. One possibility is if f of x has no roots, well, then I'm done, right? If it has no roots, then that means it has 0 roots, and 0 is less than or equal to n plus 1, right? The idea is that 0 is less than or equal to n plus 1. Great, we're done. So the other possibility is if f of x has a root, so let's say we'll call this root a in f, then I know that x minus a divides f of x by our theorem. So what does that tell me? So hence, I can write f of x is equal to x minus a times g of x. Well, what do I know about g of x? The degree of g of x has to equal n. Well, now I can use my inductive hypothesis. I know if the degree of g of x is equal to n, I know that g of x has at most n roots, right? So I could say hence, f of x has roots a plus all the roots of g of x, and there are going to be at most n of those. Right, they're going to be at most n of these. And what I can then conclude is I can say thus, f of x has at most n plus 1 roots. Right, it has that root a, and it has however many roots g of x has. And now, one question you might ask, and I'll make room for this in a second, is how do I know I've gotten all the roots of f of x? So let's try to answer that question. So I'll say if x equal to b is some other root, well, what do I know? Then x minus b is going to divide f of x. So x minus b has to divide x minus a times g of x. And now, since x minus b, degree 1 polynomials are always irreducible, I can say, well, that means that x minus b has to divide x minus a, or x minus b has to divide g of x, right? In other words, x minus b is equal to x minus a. I'll let you check this as an exercise, or b is a root of g of x, right? So we see right away that if I have some other root, then it's either going to be a or it's going to be a root of g of x. The idea here being that if x minus b divides g of x, if and only if b is a root of g of x by our previous theorem. Okay, so now we're ready for some examples. So the one example I'd like to actually talk about is where this theorem fails. So you might ask, well, is it necessary for f to be a field? Well, the answer is going to be yes. If we're not working in a field, let's see what happens. I'm going to consider this example. f of x is x squared minus 1, and this is a polynomial where we're viewing the coefficients as elements of z8. So z8 is not a field, right? Remember, the idea is that z mod p is a field if and only if p is prime. That's something we proved kind of in a much earlier video. So 8 is not a prime, so z mod 8 is not a field. In particular, it has zero divisors, like numbers like 2, 4, and 6. These are zero divisors. They're not units in z mod 8. They can't be inverted under multiplication, just as a quick review. Okay, so what are some roots of this polynomial? I might notice that f of 1 is equal to 1 squared minus 1, so that's 0. I might notice f of 3 is 3 squared minus 1, so that's going to be 9 minus 1. That's 8. That's equal to 0 in z mod 8. I might notice f of 5 is 5 squared minus 1. So this is going to be 25 minus 1. So this is 24. That's equal to 0 in z mod 8. And then I might notice f of 7 is equal to 7 squared minus 1. So this is 49 minus 1. That's 48. That's equal to 0 in z mod 8. So the thing is, f of x has degree 2. But the important thing is it has 4 roots in z mod 8, right? So if we're not working over a field, we can't really predict how many roots the polynomial is going to have necessarily. Or at least we can't put an upper bound on the number of roots necessarily. Now we're ready to explore a few corollaries of the theorems we've just proved. So first, I'll consider a polynomial f of x, whose coefficients come from a field capital F, and I'll assume that the degree of f of x is greater than or equal to 2. And the first corollary is that f of x is irreducible implies that f of x has no roots in our field capital F. And the idea being that if you're a polynomial that has a root, right? So say x equal to a is a root, then you're divisible by x minus a, and that means you can be factored into polynomials of smaller degree, which means you're reducible, means you're not irreducible. Okay, so the one thing I want to point out is that the converse of this theorem is false, right? So there are polynomials that have no roots, but are reducible. So let's kind of explore that a little bit. So I'll consider the polynomial f of x is x to the fourth plus 2x squared plus 1 in q bracket x. This polynomial is reducible. Why? Well, this polynomial factors as x squared plus 1 times x squared plus 1, right? So I can factor it as lower degree polynomials. And this polynomial has no roots. Well, why is that? Well, if I look at f of r, I'm going to get r to the fourth plus 2r squared plus 1. That's going to be bigger than 0. And this is true for all r in q. Okay, so the converse is false. So just to be clear, I've written the converse at the bottom here in red, because red is bad. I'll say f of x has no roots implies f of x is irreducible. This is in general a false statement, right? And we have the counterexample right above. So the next natural question to ask is going to be, is this converse ever true, right? Is it possible to, have some true version of this converse? Okay, so it turns out that this converse is true under one circumstance. Well, so we'll say that f of x is a polynomial whose coefficients come from a field, and we'll assume that the degree of f of x is either 2 or 3. So if the degree of f of x is either 2 or 3, then the converse of the previous corollary does hold. That is, we get an if and only if statement. So we'll say that f of x is irreducible if and only if f of x has no roots in f. So this is pretty powerful, because if I want to show that a polynomial is irreducible, and I know the polynomial only has degree 2 or 3, then all I have to do is rule out the fact that f of x has roots. Okay, so let's prove this. So the first thing I'll point out is that the forward direction is just the previous corollary. The backwards direction, we're going to prove using the contrapositive, right? So the idea is we want to show that f of x has no roots, implies that f of x is irreducible. We'll show the contrapositive of that statement, namely that f of x is reducible, implies that f of x has a root. Okay, so let's begin our proof. So f of x is reducible. Well, that implies that f of x can be written as g of x times h of x. And we know that g of x and h of x are both polynomials in f bracket x. And the other thing that I know is that these guys have smaller degree. Right? So in other words, this tells me that either the degree of g of x is 1, or the degree of h of x is 1, or both. Right? So if I take a quadratic and it's reducible, that means it factors into two linear polynomials. If I take a cubic polynomial and it's reducible, that means it factors into a linear polynomial times a quadratic polynomial. So we end up with one of these factors has to be degree 1. So I'll say, without loss of generality, I'll assume that g of x has degree 1. Right? So I'll assume that the degree of g of x is equal to 1. Right? So in other words, g of x is equal to ax plus b for some a and b in my field. And a is non-zero because this is a degree 1 polynomial. Well, then I could find the root pretty easily for g of x. So then if I plug in x is equal to negative a inverse b is a root of g of x, and thus is a root of f of x. Right? The idea is that f of negative a inverse b is going to be g of negative a inverse b times h of negative a inverse b, which is going to be 0 times h of negative a inverse b, which is equal to 0. And so I've proved the backwards direction. Okay, so finally we'll apply this theorem to an example. So let's consider the polynomial f of x is 3x squared plus 2x plus 1 in Z5 bracket x. So this is a quadratic polynomial. It's a polynomial of degree 2. So according to our theorem, if I want to determine whether or not this polynomial is irreducible, all I need to do is check, does this polynomial have any roots in Z5? And this is kind of nice because Z5 only has 5 elements, namely 0, 1, 2, 3, and 4. So I just go one by one and plug these elements in, right? So I'll say f of 0 is 1. So that's not a root. F of 1 is 1 if I do the math. So 1 is not a root. F of 2 is equal to 2. So 2 is not a root. F of 3 is equal to 4. So 4 is not a root. And f of 4 is equal to 3. So 4 is not a root. Okay, so what does that tell me? That tells me that f of x has no root in z mod 5 or z5. So f of x is an irreducible polynomial. This polynomial cannot be factored. So this is kind of the power of this theorem, right? The idea is if I have a degree 2 or 3 polynomial, if I want to determine whether or not it's irreducible, I just check, does the polynomial have any roots? If I can prove that the polynomial doesn't have any roots, then I know right away that the polynomial is irreducible. We saw again in our a few minutes ago that this fails if the polynomial has degree 4. But if it's degree 2 or degree 3, to check for irreducibility, all we have to do is look for roots.